Welcome friends. In this module we discuss more problems on law of large numbers and central limit theorem. We already discussed the following: Chebyshev's inequality. Let x be a random variable for which the mean mu and variance sigma square exists. Then for any positive number t, probability of modulus of x minus mu greater than or equal to t sigma less than or equal to 1 by t square, or probability of modulus of x minus mu less than or equal to t sigma greater than or equal to 1 minus 1 by t square. Bernoulli's law of large numbers, BLLN. Consider a random experiment with only two possible outcomes, success and failure. Let P be the probability of success. It is assumed that it remains unchanged from trial to trial. Let n independent trials of the experiment being considered. Let xn be the number of successes in these n trials. Bernoulli's law of large numbers, BLLN, states that for any epsilon greater than 0, probability of modulus of xn by n minus p less than epsilon tends to 1 as n tend to infinity. Weak law of large numbers, WLLN. Let x1, x2, etc. xn be a sequence of random variables with expectation of x I equal to mu I for I equal to 1, 2, etc. n. Let Sn equal to x1 plus x2, etc. plus xn. Mn equal to mu1 plus mu2, etc. plus mun, and Bn equal to variance of x1 plus x2, etc. plus xn. Then probability of modulus of Sn by n minus Mn by n greater than or equal to epsilon tends to 0 as n tend to infinity, provided Bn by n square tends to 0 as n tend to infinity. Lindbergh-Levy form of central limit theorem. If x1, x2, etc. xn are independent and identically distributed random variables with the expectation of xi equal to mu and variance of xi equal to sigma square for all I, then the sum Sn equal to x1 plus x2, etc. plus xn is asymptotically normal with mean and mu and variance and sigma square. That is, Zn equal to Sn minus n mu divided by root n into sigma follows n01 as n tend to infinity. Problem 1. To estimate the proportion of engineers who have studied abroad and the estimate to be correct within 5% with probability 0.90 or more. How large a sample would be? 1. If there is no idea about the true proportion. 2. If it is known that the true proportion is less than 0.1. Solution. Let xn be the number of engineers who have studied abroad out of n. Then the frequency ratio is xn divided by n. Let p be the actual proportion. To find the minimum number of samples so as to estimate the value of p within 5% of the actual value with a probability greater than or equal to 0.90. If there is no idea about the actual proportion, then by Bernoulli's law of large numbers we have probability of modulus of xn by n minus p less than epsilon greater than 1 minus 1 divided by 4 n epsilon square. Put epsilon equal to 0.05, then probability of modulus of xn by n minus p less than 0.05 greater than 1 minus 1 divided by 4 into n into 0.05 square. To get the number of samples required so as the above probability greater than 0.90, we have to find n such that 1 minus 1 divided by 4 into n into 0.05 the square equal to 0.90. This implies 0.10 equal to 1 divided by 4 into n into 0.05 the square. This implies n equal to 1 divided by 4 into 0.10 into 0.05 square. This implies n equal to 1000. 2. If it is known that p less than 0.1, then probability of modulus of xn by n minus p less than epsilon greater than 1 minus 0.1 into 0.9 divided by n into epsilon square. Put epsilon equal to 0.05, then p of mod xn by n minus p less than 0.05 greater than 1 minus 0.1 into 0.9 divided by n into 0.05 square. To get the number of samples required so as the above probability greater than 0.90, we have to find n such that 1 minus 0.1 into 0.9 divided by n into 0.05 square equal to 0.90. This implies n equal to 0.1 into 0.9 divided by 0.1 into 0.05 square. This implies n equal to 360. Problem 2. Let sequence xk be mutually independent and identically distributed random variables with mean, mu and finite variance. If Sn equal to x1 plus x2 etc. plus xn, prove that the weak law of large numbers does not hold for the sequence Sn. Solution. We are considering the sequence Sn. Now, the variables are S1, S2 etc. Sn. Here expectation of Si equal to expectation of x1 plus x2 etc. plus xi, variance of Si equal to variance of x1 plus x2 etc. plus xi, Bn equal to variance of S1 plus S2 plus S3 plus etc. plus Sn, that is equal to variance of x1 plus x2 plus x1 plus x2 plus x3 plus etc. plus x1 plus x2 plus etc. plus xn, that is equal to variance of nx1 plus n minus 1 into x2 plus n minus 2 into x3 plus etc. plus xn. Since xi's are independent, Bn equal to n square into variance of x1 plus n minus 1 all square into variance of x2 plus n minus 2 all square into variance of x3 plus etc. plus variance of xn. Also, since xi's are identically distributed, variance of xi's are same for all I. Let it be sigma square. Then Bn equal to n square plus n minus 1 all square plus n minus 2 all square plus etc. plus 1 into variance of xi, that is equal to n into n plus 1 into 2n plus 1 all divided by 6 into sigma square. Therefore, Bn by n square is equal to 1 by n square into n into n plus 1 into 2n plus 1 all by 6 into sigma square. Then as n tend to infinity, Bn divided by n square, that is equal to 1 plus 1 by n into 2n plus 1 all divided by 6 into sigma square tends to infinity. Hence, WLLn cannot hold good for the sequence Sn. Problem 3. Examine whether WLLn hold for the sequence of independent random variables xi for I equal to 1, 2, 3 etc., where p of xi equal to plus or minus square root of 2i minus 1 equal to 1 by 2. Solution. Expectation of xi equal to minus square root of 2i minus 1 into 1 by 2 plus square root of 2i minus 1 into 1 by 2, that is equal to 0 for all I. Expectation of xi square equal to minus of square root of 2i minus 1 the whole square into 1 by 2 plus square root of 2i minus 1 the whole square into 1 by 2, that is equal to 2i minus 1 for all I. This implies variance of xi equal to 2i minus 1 for all I. Therefore, Bn equal to variance of x1 plus x2 plus x3 plus etc. plus xn, that is equal to 1 plus 3 plus 5 plus etc. plus 2 n minus 1, sum to n terms, that is equal to n into 2n minus 1 plus 1 all divided by 2, that is equal to n square. Therefore, Bn divided by n square is equal to n square divided by n square, that is equal to 1. So, Bn by n square does not tend to 0 as n tend to infinity. So, WLLn does not hold for the given sequence xi. Problem 4. Examine whether WLLn hold for the sequence of independent random variables xk where k equal to 1, 2 etc., where probability of xk equal to plus or minus 2 raised to k, that is equal to 2 raised to minus of 2k minus 1, probability of xk equal to 0, that is equal to 1 minus 2 raised to minus 2k. Solution. Here expectation of xk equal to 2 raised to k into 2 raised to minus 2k plus 1 plus minus 2 raised to k into 2 raised to minus 2k plus 1 plus 0 into 1 minus 2 raised to minus 2k, that is equal to 0. Expectation of xk square, that is 2 raised to k the whole square into 2 raised to minus of 2k plus 1 plus minus 2 raised to k the whole square into 2 raised to minus of 2k plus 1 plus 0 into 1 minus 2 raised to minus 2k, that is equal to 2 raised to 2k into 2 raised to minus of 2k plus 1 plus 2 raised to 2k into 2 raised to minus of 2k plus 1, that is equal to 2 raised to 2k plus 1 into 2 raised to minus of 2k plus 1, that is 2 raised to 0, that is equal to 1. This implies variance of xk equal to expectation of xk square minus expectation of xk the whole square, that is equal to 1 minus 0, that is 1. Therefore, Bn variance of x1 plus x2 plus x3 etc. plus xn, that is equal to 1 plus 1 plus etc. plus 1 n terms, that is equal to n. Therefore, Bn divided by n square equal to n divided by n square, that is 1 by n. So, Bn divided by n square tends to 0 as n tend to infinity. So, WLLn hold for the given sequence xk. Problem 5. Test whether WLLn hold for the sequence of independent random variables xn where p of xn equal to plus or minus 1, that is 1 by 2 into 1 minus 2 raised to minus n for n equal to 1, 2 etc. Solution. Expectation of xn equal to 1 into 1 by 2 into 1 minus 2 raised to minus n plus minus 1 into 1 by 2 into 1 minus 2 raised to minus n, that is equal to 0 for all n. Expectation of xn square equal to 1 square into 1 by 2 into 1 minus 2 raised to minus n plus minus 1 square into 1 by 2 into 1 minus 2 raised to minus n, that is equal to 1 minus 2 raised to minus n for all n. Variance of xn equal to 1 minus 2 raised to minus n for all n. Therefore, Bn equal to variance of x1 plus x2 etc. plus xn, that is equal to 1 minus 2 raised to minus 1 plus 1 minus 2 raised to minus 2 plus etc. plus 1 minus 2 raised to minus n, sum to n terms, that is equal to n minus of 2 raised to minus 1 plus 2 raised to minus 2 plus etc. plus 2 raised to minus n, that is equal to n minus of 1 by 2 plus 1 by 2 square plus etc. plus 1 by 2 raised to n, that is equal to n minus 1 by 2 into 1 minus 1 by 2 raised to n divided by 1 minus 1 by 2, that is equal to n minus of 1 minus 1 by 2 raised to n. Therefore, Bn divided by n square is equal to n minus of 1 minus 1 by 2 raised to n divided by n square, that is equal to 1 by n minus 1 by n square plus 1 by n square into 1 by 2 raised to n, which tends to 0 as n tend to infinity. So, WLLn hold for the given sequence xn. Problem 6. A distribution with the unknown mean mu has variance equal to 2. By using central limit theorem, find how large a sample should be taken in order that the probability will be at least 0.90 that the sample mean will be within 0.4 of the population mean. Solution. Let x1, x2 etc. xn be the randomly taken sample from the population. To find the minimum number of samples required so as probability of modulus of x bar minus mu less than 0.4 greater than or equal to 0.90, let it be 1. Since x1, x2 etc. xn are randomly taken, they are independent. Given population mean is mu and variance is 2. Then by central limit theorem, x1 plus x2 etc. plus xn follow normal n mu 2n for large n. This implies x bar follow normal mu 2 divided by n. This implies u equal to x bar minus mu divided by square root of 2 by n follow n01 as n tend to infinity. From standard normal table, we get probability of modulus of x bar minus mu divided by square root of 2 by n less than 1.645 equal to 0.90. This implies probability of modulus of x bar minus mu less than 1.645 into square root of 2 by n equal to 0.90. Let it be 2. From 1 and 2, we get for the required number of samples, 1.645 into square root of 2 by n less than or equal to 0.4. This implies n greater than or equal to 1.645 into square root of 2 divided by 0.4 the square. This implies n greater than 33.82. Hence, the minimum number of sample required is 34. Problem 7. 30 unbiased dice are thrown. Find the approximate probability that the sum of the numbers shown is in between 90 and 120 using central limit theorem. Solution. Let x1, x2, etc. x30 be the numbers shown by the 30 dice. Each unbiased die can show any of the numbers from 1 to 6, each with probability 1 by 6. Hence, expectation of xi equal to 7 divided by 2 for I equal to 1, 2, etc. and variance of xi equal to 35 divided by 12 for I equal to 1, 2, etc. Sum of the numbers shown Sn equal to x1 plus x2 etc. plus x30. This implies expectation of Sn equal to 30 into 7 divided by 2, that is 105, and variance of Sn equal to 30 into 35 by 12, that is 175 divided by 2. By central limit theorem, Sn follow normal with mean 105 and standard deviation square root of 175 divided by 2. So, probability of 90 less than Sn less than 120 equal to probability of 90 minus 105 divided by square root of 175 by 2 less than Sn minus 105 divided by square root of 175 by 2, that is less than 120 minus 105 divided by square root of 175 by 2. That is equal to probability of minus 1.604 less than z less than plus 1.604, where z follow n01. That is equal to 2 times probability of 0 less than z less than 1.604. That is equal to 2 into 0.4456, that is 0.8912. Problem 8. 30 real numbers are randomly selected from the interval 0 to. Find the approximate probability that the sum of these numbers greater than 25. Solution. Let x1, x2, etc. x30 be the numbers randomly drawn. Let xi denote the ith number drawn. Since it is a real number randomly drawn from 0 to, xi follows rectangular distribution over 0 to. Hence, expectation of xi equal to 2 plus 0 by 2, that is 1, and variance of xi equal to 2 minus 0 square by 12, that is 4 divided by 12, that is equal to 1 by 3 for all I equal to 1, 2, etc. 30. Sum of the numbers drawn Sn equal to x1 plus x2 etc. plus x30. Then expectation of Sn equal to 30 into 1, that is 30, and variance of Sn equal to 30 into 1 by 3, that is 10. By central limit theorem, z equal to Sn minus 30 divided by root 10 follows n01. Hence, p of Sn greater than 25, that is equal to p of z greater than 25 minus 30 divided by root 10, that is p of z greater than minus 1.58, that is equal to 0.9429. Now, let us summarize. The module is concentrating more problems based on central limit theorem and laws of large numbers. An in-depth knowledge in the areas of application and problem solving based on these theorems are expected through this module. Before moving to the next module, please try to answer the following questions. A. Let x1, x2, x3, etc. xn are IID Poisson random variables with parameter lambda equal to 3. Use central limit theorem to estimate p of 280 less than or equal to Sn less than or equal to 350, where Sn equal to x1 plus x2 plus x3 etc. plus xn and n equal to 90. B. Test whether WLLN hold for the sequence of independent random variables xi for I equal to 1, 2, 3 etc., where p of xn equal to 1 by root n, that is equal to 2 by 3, p of xn equal to minus 1 by root n equal to 1 by 3 for n equal to 1, 2 etc. C. Examine whether WLLN hold for the sequence of independent random variables xn for n equal to 1, 2, 3, etc., where p of xn equal to plus or minus 1, that is equal to 1 minus 2 raised to minus n divided by 2, p of xn equal to plus or minus 2 raised to minus n equal to 2 raised to minus n minus 1 for n equal to 1, 2, etc. D. Lifetime of a machine is distributed as exponential with mean 8 years. What is the probability that the average lifetime of a random sample among the machines is at least 10 years? The books for your reference are Introduction to Probability Models, Sheldon M. Ross, Academic Press, 1997. Introduction to Mathematical Statistics, S. C. Gupta, V. K. Kapoor, Sultan Chand and Sons, 2003. A First Course in Probability, T. K. Chandra, D. Chatterjee, Narosa, 2003. A First Course in Probability, Sheldon M. Ross, Pearson Education, 2007. Probability and Statistics for Engineers, R. A. Johnson, PHI, 2005. Hope you enjoyed this session. See you next time. Until then, bye.